Hello, in this video I'd like to talk about matrix determinants, and possibly the most intuitive way of thinking about determinants is geometrically. So what does a matrix do geometrically? Well, if we imagine all of the points in space, those have coordinates, and those coordinates form vectors. And we can imagine applying our matrix to each of those vectors, and that's going to give us a new set of coordinates. And so what a matrix does is it takes points and it moves them somewhere. And we can imagine taking all of the points of an object and moving them according to this matrix transformation. There's a wide variety of things that we can do with matrices. We can stretch objects out, we can rotate objects, but matrix operations are also very limited. We can't take objects and stretch them out by different amounts in different areas. Everything gets stretched out the same amount throughout all of space. And this stretching amount, the amount that the volume or area, depending on however many dimensions we're in, gets multiplied by, that is the determinant. So for instance, if we stretch space out, the determinant is just how much we stretched space out by. If we rotate an object, well, that's not going to affect the volume, and so the determinant of a rotation matrix is going to just be 1, because we're multiplying the volume by 1. If we take an object and flip it inside out or backwards, then that's actually something that it's actually nicer mathematically to take that into account. And so we want to say that something has a negative determinant if it flips things inside out. And from this geometric interpretation of determinants, we actually get one of their most important algebraic properties, that the determinant of the product of two or more matrices is just the product of the determinants. We can imagine it this way. Suppose that we have two transformations that we want to apply to a particular object. If we were to apply the matrix AB to a particular vector, well, it's first going to apply B to that vector, and then it's going to apply A to the result. When we apply B to a particular object, that's going to multiply its area or volume by the determinant of B. And then when we apply A to the result, it's going to multiply the resulting volume by the determinant of A. And so therefore, multiplying by AB is going to take the volume and first multiply it by the determinant of B, and then multiply it by the determinant of A. In other words, this whole operation is going to multiply the volume by the product of these determinants. And this property forms an important part of all sorts of properties of determinants and proving all sorts of things about them. And it's actually going to form the foundation of the first way in this video I'm going to talk about calculating the determinant of a matrix. So an important fact, if we take a square invertible matrix and we reduce it all the way into reduced row echelon form, it's going to be a square invertible matrix in reduced row echelon form. And there's only one of those, the identity matrix. That is to say that we can take any matrix M and multiply it by a series of elementary row operation matrices, and the result is going to be the identity matrix. And we can actually flip this fact around by multiplying both sides by the inverse of this product here. In other words, M is going to be the inverse of this product of elementary row operations. Now, if we want to take the inverse of a product of matrices, well, it's going to be the reversed product of the inverses of those matrices. And you can see that this is the case if you replace the M in this formula with this particular expression here. So this here is the matrix that I claimed M was, and we can see that these two cancel, and because they go away, because they've canceled, E2 and E2 inverse are then allowed to cancel, and then E3 and E3 inverse will be able to cancel, And then finally, En and En inverse will be able to cancel, and so we'll get the identity matrix. So this here is a formula for our original matrix M. In other words, because the inverse of an elementary row operation matrix is also an elementary row operation matrix, every square invertible matrix is going to be the product of a series of elementary row operation matrices. So if we want to figure out the determinant of M, all we need to do is figure out the determinants of each of the elementary row operation matrices that together multiply to give us M, and then multiply those determinants together. Suppose that we were looking at the matrix for the elementary row operation that takes row 1 and adds twice row 2 to it. Well, in order to figure out what the matrix is for a particular row operation, all we need to do is apply that row operation to the identity matrix. The resulting matrix actually corresponds to a skew in space, as we can see here. And because skewing an object doesn't affect its volume, this matrix operation and any elementary row operations like it are not going to affect the volume of an object. And therefore, these sorts of elementary row operation matrices are going to have determinant 1. On the other hand, suppose that we have a row operation that takes row 1 and multiplies it by 3. We can figure out the matrix for this row operation simply by applying this operation to the identity matrix. This matrix here corresponds to stretching space out in the x direction by a factor of 3, and therefore is going to multiply the volume of any object by 3. So the determinant of these sorts of operations is just the amount that we multiply that particular row by. Finally, if we have a row operation that interchanges two of the rows, its matrix can be found by taking the identity matrix and interchanging two of its rows. Geometrically, this corresponds to mirroring over the plane y is equal to x, and because we have mirrored it, that means that the determinant is -1. So suppose that we take a particular invertible square matrix and row reduce it to get the identity. Here I'm going to use the same example from my matrix inverses video, because I already have it row reduced. So as we can see, applying this series of row operations, that is multiplying by these elementary row operation matrices, takes our original matrix and turns it into the identity matrix. Well, if we reverse that process, we're going to get from the identity matrix back to our original matrix. We will need to apply the inverse operations in reverse order. So we start with the inverse of this operation here, that is multiply row 3 by 7. Then we take this operation and invert that. Well, this operation is its own inverse. The inverse of this skewing operation is to subtract 4 times row 2 from row 1, because row 2 isn't changed in this operation. The inverse of this operation is its own inverse. And then finally we add row 1 to row 2. And we get back to our original matrix. So as we can see, multiplying these elementary row operation matrices in this appropriate order, it's actually reversed. It's going to be, we're going to multiply this one on the right and this one on the left, because the order that matrices get applied is reversed. But multiplying these matrices together gives us, well, it starts from the identity matrix and it gives us this matrix here. In other words, multiplying these matrices together gives us this matrix here. So what that means is that the determinant of this matrix is just going to be the product of the determinants of each of these row operations. The determinant of this operation is 7. The determinant of this operation is -1. This is a skew, so it has determinant 1. This is an interchange, so it has a determinant -1. And this is another skew. So all in all, the determinant is going to be this product, which is just going to be 7. So if you are row reducing a matrix anyway, you get, for free, the determinant of the original matrix. This is actually a little bit more complicated than it has to be. You could stop at this stage here when you have an upper triangular matrix, and it's actually very easy to calculate the determinant of one of these. You just multiply the elements along the diagonal, and then you still have to account for the matrices that you've already multiplied by. So this is going to add a factor of -1. Another very useful way of thinking about determinants is in terms of a fairly complicated formula. So here, in order to calculate the determinant of a particular matrix M, we take the sum over all permutations on the numbers from 1 to n. So here, this lowercase sigma is going to represent some function from the numbers 1 through n to the numbers 1 through n. And this function has to permute those numbers. It can't take two numbers to the same number, and it can't miss out on any numbers. So this has to be a function that just shuffles the numbers 1 through n around. And then we take the sign of that particular permutation, and this is a number that's either +1 or -1, depending on the number of swaps that this particular permutation does. And we multiply that by the product over all values of I from 1 to n of the sigma of ith, comma ith element of M. So let's see this in action with just a basic 2x2 matrix. It turns out that there are only two permutations on the numbers 1 and 2. We can either keep them as they are. We can have the identity function, f of x is equal to x, or we can swap them around. Now, when I'm looking at these particular types of permutations, I like to think about the corresponding permutation matrix. We can imagine an operation on a vector that takes the elements of row 1 and moves them to row 1, and the elements of row 2 and moves them to row 2, or takes the elements of row 1 and moves them to row 2, while taking the elements of row 2 and moving them to row 1, permuting the elements of a vector according to this particular permutation function. And that matrix is going to be, well, in this case, it does nothing to the vector, so it's going to be the identity matrix. And this matrix here is going to be the row swap matrix. The sign of a particular permutation is, and I realize this is recursive, it's the determinant of these matrices here. And we can write any of these permutation matrices as the product of individual pairwise swaps. And so the determinant of each individual pairwise swap is going to be -1. So the product of those is either going to be plus or minus 1, depending on whether it's an even or odd number of swaps. In this case, it's 0 swaps, so it's an even number of swaps, and therefore the sign is +1. We take -1 to the power of 0, and then this is 1 swap, which is an odd number of swaps, and therefore the sign is -1. And then we simply take the corresponding elements of our original matrix. If we imagine our original matrix looking like this, we're simply taking M11, we have to read it backwards, times M22 for this product here. And then the product for this permutation is going to be M21 times M12. And so together, these two terms give us the determinant of the original matrix. And perhaps you've seen this formula before. This is the determinant formula for a 2 by 2 matrix. Typically it's presented, if we're looking at a matrix A, B, C, D, then the determinant is going to be positive A times D minus B times C times B. So that's the 2 by 2 case. Let's take a look at the 3 by 3 case. There are 6 possible permutation functions. So let's start by taking a look at 3 of these permutations. This first permutation, the identity operation, the function that doesn't do anything, is the product of 0 flips, and so therefore has sign of +1. And this product here is going to be m11 times m22 times m33. This permutation here, which just flips 2 and 3, it leaves 1 alone, corresponds to this particular matrix here. This is a product of 1 flip and therefore has a sign of -1. And it corresponds to m11, m32, m23. This permutation switches 1 and 2 and corresponds to this particular permutation matrix here. It consists of 1 flip and therefore has a sign of -1 and corresponds to the product m21, m12, m33. Now let's look at the remaining 3 permutations. This permutation here actually consists of 2 permutations, and we can see that it's actually this permutation here where we've swapped row 1 and row 2. And so the sign of this particular permutation is actually going to be -1 to the power of 2, so +1. And it corresponds to the product of the elements m21, m32, m13. This permutation here corresponds to this matrix, and it's actually just switching rows 1 and rows 3. So it is a single swap, so it has sign -1, and it's going to be m31, m22, m13. And finally, this permutation here, we can see is actually this permutation where we've swapped rows 1 and rows 2, and therefore is a product of 2 swaps, and so has sign +1 and corresponds to the product m31, m12, m23. And so together, when we add up these 6 terms, we get a formula for the determinant of a particular matrix. And this corresponds to, you've probably seen a different way of calculating the determinant of a 3 by 3 matrix, where you copy over the first 2 columns and then look at some diagonals. These diagonals count positively towards the determinant, and these diagonals count negatively towards the determinant. And we can see that's actually exactly what's happening here. This diagonal, we're taking the product of the entries along this diagonal, and it's counting positively towards the determinant. We're taking the entries along this diagonal, wrapping around, and the product of the entries along that diagonal is counting positively towards the determinant. And finally, we take this third diagonal, wrapping around, and the product of the entries in these locations are counting positively towards the determinant. And then we do these anti-diagonals and count them negatively. So we have this one, the product of the entries at these 3 locations is being multiplied by -1. It's counting negatively towards the determinant. The product of these three entries wrapping around is going to count negatively towards the determinant. And finally, the product of these three entries wrapping around is going to contribute negatively towards the determinant. And so we see that these six terms here correspond to these six matrices here, and we're looking at the elements that have ones in them in our original matrix and multiplying those elements together, and then we're multiplying by either +1 or -1, depending if it's this way diagonal or this way diagonal. In other words, depending on the sign of the permutation. Now, this is a really great way of calculating determinants in 3 dimensions, but it might lead you to believe that this formula works in other dimensions. It kind of seems like it works in 2 dimensions, but if you actually try to formalize the analogy, it doesn't quite work. And when you go up to 4 dimensions, you're actually going to miss out on a bunch of permutations. In 4 dimensions, there are 4 factorial, which is 24 permutations, but counting the diagonals this way and counting the diagonals this way, there's only going to be 4 plus 4, which is 8 different diagonals, so we're going to miss out on most of the permutations. I'm going to put up on screen, because I'm not going to write this out, I'm going to put up on screen the corresponding formula for the determinant in 4 dimensions. There's one more technique that I'd like to talk about in this video, and it's perhaps the most commonly presented way of calculating the determinant of an arbitrary n by n matrix, and that's expansion along a particular row or column. So for instance, suppose that I have the matrix 1, 2, 3, 4, 5, 6, 7, 8, 9, and I want to calculate its determinant. Well, step 1, I'm actually going to need to write out a checkerboard pattern of pluses and minuses to use as reference. So I'm going to start by picking a row or a column. I'll do the first row as an example, but then I'll also do another example. We start with this one here, and we're going to look at the corresponding sign from this checkerboard grid of signs, and then we're going to imagine getting rid of the corresponding row and column corresponding to this 1 here. That's going to leave us with a 2 by 2 matrix, or an n-1 by an n-1 matrix in higher dimensions, and we need to take the determinant of that. Now we look at the next entry along that particular row, and we look at the sign from this checkerboard grid, and then we multiply by the determinant of the matrix that's left over. And then finally, we look at the last entry of the row and multiply it by the corresponding sign, and then multiply it by the determinant of the matrix that's left over when we get rid of the first row and the third column. If we do these calculations, so it turns out that this original matrix actually has determinant 0, and we should get the same answer when we expand along any other row or any other column. So for instance, let's expand along this middle column here. We're going to do the same thing. We'll look at each of the entries, we'll look at the grid of pluses or minuses, and then we'll look at the determinant of the remaining matrix. So this 2 gets multiplied by -1, and also multiplied by the determinant of the matrix 4, 6, 7, 9. This 5 then gets multiplied by +1, and also the determinant of the matrix 1, 3, 7, 9. And then finally, this 8 here gets multiplied by -1, and also the determinant of the matrix 1, 3, 4, 6. And as we can see, when we do this calculation, we also wind up getting 0. So no matter how you slice it, the determinant of this original matrix is equal to 0. And it's clear how we can extend this procedure into arbitrary higher dimensions. We simply get a higher dimensional grid of pluses and minuses. We pick a particular row and a particular column, and then we expand along that row or column, picking out the entries along that row or column, multiplying by the appropriate sign, and then taking the determinant of the matrix that's left over when we get rid of the row and the column corresponding to that particular entry. In 4 dimensions, the determinant of this matrix here is going to wind up being, it's going to be a 3 by 3 matrix, and so we're taking the determinant of a 3 by 3 matrix. And so in order to do that, you need to do a process like this. It's recursive, and you have to apply this process all the way down. So hopefully at some point you can stop and use another rule to calculate the determinant. Oh, it's kind of obvious that, you know, the determinant of this matrix should be 0 or something like that. But if you can't, then you're stuck calculating 2 by 2 determinants in order to calculate 3 by 3 determinants, in order to calculate 4 by 4 determinants, in order to calculate 5 by 5 determinants, all the way up until however dimensions you're at. So it's actually a long and very tedious and complicated process if you're actually trying to do this and can't use other rules about determinants to save yourself a little bit of work. Now, I briefly want to show you something that I thought was true when I saw this particular formula, and based on this other wrapping around way of calculating determinants in 3 dimensions, but it's actually not true. One of the things that I thought you could do is ignore this grid of signs here, and instead, when we were calculating this particular entry of the summation, we simply got rid of the corresponding row and column and viewed the resulting matrix in a wrapped around fashion. That is, instead of looking at this matrix here as 4, 6, 7, 9, instead viewing it wrapped around as 6, 4, 9, 7. And it turns out that this actually works. It works in this 3-dimensional case. By applying this, we negate this, we multiply this term by -1 because we turned it from a negative to a positive, and we also switched 2 of the columns of this matrix here, which multiplies the determinant by -1. And so we're multiplying this term here by -1 times -1, which isn't going to change the term at all. So in 3 dimensions, this sort of wrapping around process actually does work. The problem is, if you check this in 2 dimensions, it doesn't work in 2 dimensions. And if you check this in 4 dimensions, it doesn't work in 4 dimensions. If you check it in 5 dimensions, it does work in 5 dimensions. In fact, this procedure of looking at wrapped around matrices, wrapped around submatrices, as opposed to looking at just getting rid of the row and the column, actually lets you calculate determinants correctly in odd numbered dimensions. And if you want to get this formula to work in even numbered dimensions, you have to bring back this checkerboard pattern of pluses and minuses. But the whole point of this was to avoid referring to this checkerboard pattern of pluses and minuses, so I really don't recommend the wraparound technique when you are expanding along particular rows and columns. So that's all of the techniques that I'd like to present in this video. There are, of course, a few more. Why is it obvious that this matrix 1, 2, 3, 4, 5, 6, 7, 8, 9, why is it obvious that that matrix isn't invertible? Why is it obvious that it has determinant 0? That's a question for another video. So if you were watching this video just to learn about matrix determinants, thanks for watching, and I hope to see you in a future video. But if you're here for a bit more of a challenge, I actually have a challenge problem for you. what are the possible determinants of an n by n matrix? So this is going to depend on n. What are the possible determinants of an n by n matrix, all of whose entries are zeros and ones, and there's at most 2 ones in each row and each column? So I'll let you think about this problem. It was presented to me on math.stackexchange, and I thought it was a really fun problem, and I will answer this problem in a future video.